All right, let's get started. So real fast, just to go over the agenda again, we're basically going to do a very quick overview over BlazingSQL and the Rapids ecosystem. And then from there, Tom is really going to take up the majority of this talk, showing everyone off the demo use cases that we've put together. And we're effectively going to be going over an enterprise-style workload or series of use cases or workloads, if you will, that really leverage, a lot of BlazingSQL, but really the rest of the Rapids ecosystem and stack. So most of these use cases will start out with, ETL or ELT steps that are very SQL dominant or data frame API dominated. And then after that, they'll go over to some other workflow, and Tom's going to be showing that off. And then after he does the hands-on part, Tom's actually going to scale up utilizing access to our private beta of our web application, or of app.blazingsql.com and Blazing Notebooks, which lets you create, large-scale multi-GPU instances. So he'll show what it really looks like to scale up from something that's going to be about 1 gigabyte, which is what we're going to be doing in the hands-on demos, to 1 terabyte, and really looking at it in an enterprise context. So real fast, just to kind of fill you all in, I'm Rodrigo. I'm one of the co-founders and I'm CEO of BlazingSQL. We're a distributed GPU accelerated SQL engine. We've been working on accelerated SQL in GPUs for years now. BlazingSQL itself was released probably about 2 years ago this week. So, the project itself is an open source project. We've been going pretty strong for 2 years. We launched 1 month after the entire Rapids ecosystem launched. And we had actually been working on the SQL engine for quite a few months previous to that with Rapids. If you're interested in any news BlazingSQL, you can follow us on Twitter at BlazingSQL. That's where we put all of the latest and greatest information around BlazingSQL and the Rapids ecosystem that we've been involved in. And this webinar is a series that we do every other week. So if you're interested in the content that we show off here, you can always come back once every other week on Tuesdays at this same time, 11 a.m. Pacific. We will go over a new webinar. Although for December, we're probably going to change that schedule up a little bit, but we'll be posting all of those changes publicly on Twitter. So when we're thinking about BlazingSQL, and forgive me for anyone who already knows this or has been to our previous webinars, because we basically go over this at the beginning every time. But for those who aren't familiar, BlazingSQL is effectively SQL1 data frames. So the argument that we make is, what would you do if you had something as convenient as a data frame, but could also interlace data frame functionality with SQL functionality to create this really interesting, in-memory data frame that you can do all sorts of things and plug it into a variety of different packages and libraries. So this example right here is probably the most basic BlazingSQL query you could write, where if you're familiar with pandas, cuDF effectively re-implements pandas, but on the GPUs. This is a really fundamental project inside the Rapids ecosystem. I like to think about this as the linchpin of all the libraries, the cuDF data frame, because it's what connects to all the different libraries from BlazingSQL to machine learning, deep learning, etc. And so in this, if you're familiar with pandas, this would look really, really quite familiar to you, where you basically just do a .read CSV on a file, and it'll read this CSV file into a GPU memory data frame. What we can then do is we can create a table off of this data frame using bc.createTable. BC is basically just a Blazing context. We'll show you a little bit more of that in the actual demos. But this is a table that lives on top of an in GPU memory data frame. So if we're trying to do in-memory analytics or looking for things that respond to us in tens or hundreds of milliseconds, then this is really the easiest and fastest way to do it, is by creating a table off of these in-memory data frames. And now you can do all sorts of in-memory, hyper low latency, high bandwidth analytics. Where BlazingSQL gets really powerful, though, is you can also be writing these create table statements directly off of CSV files. And so we can start running queries directly off of files wherever it is that they happen to live. And that's really part of the power of BlazingSQL. So BlazingSQL itself is a component of a greater ecosystem, which is called the Rapids ecosystem. For anyone not familiar with it, Rapids is an end-to-end data science stack for accelerating data science workloads on GPUs. And the big benefit is faster, for lower total cost of ownership. And that's really what we're focused on in the Rapids ecosystem and everything that we're doing with Rapids. BlazingSQL is the SQL engine of that ecosystem. It's how you can, connect data lakes or large-scale data sets to Rapids. It's really the easiest way of doing large-scale ETL processing performantly and cost-effectively. And then Dask is what allows us to scale up this entire ecosystem from one GPU to hundreds of GPUs and beyond. Right. I think the largest BlazingSQL cluster that I'm familiar with was about 720 GPUs. And it was actually done on the Summit supercomputer. So that kind of just demonstrates how effectively these systems are at scaling up. Just to finish up real fast and then handing it over to Tom. This is a really good overview of the Rapids ecosystem, although this chart is no longer an exhaustive list. This actually there are a lot of packages that aren't demonstrated or talked about here, but really fast. Everything lives inside GPU memory in this Apache Arrow style format that we created with the entire Rapids ecosystem. BlazingSQL is the SQL engine of that. cuDF is really the data frame library so that you're able to do data frame style APIs on the same exact memory object. cuML is machine learning. So if you're familiar with scikit-learn, this is the same exact APIs re-implemented on GPUs. So you just have, GPU accelerated scikit-learn working for you. cuGraph is for anyone who's interested in graph analytics. So if you're familiar with NetworkX, same exact idea. Pandas on GPUs, scikit-learn on GPUs, NetworkX on GPUs. So you can do really accelerated graph analytics. And there's plugins with all sorts of different deep learning frameworks as well as visualization libraries. And so with all that in mind, this is a great time for Tom to start up your camera and your mic. Tom's basically going to start taking us through the use cases and the workflows, and I'll start sharing so that you can start sharing, Tom.
Alrighty, thanks, Rodrigo. Hello, everyone, and thanks for joining us. I know it's Thanksgiving week, and everybody is busy with everything else, but we hope that you guys will actually enjoy what we have for you today. So let me start sharing my screen. Please let me know when you actually can see this.
Yep, we can see it.
Awesome. All right. So first things first, we will be walking through this particular notebook today. And this notebook is actually available from our Welcome to BlazingSQL notebooks. I'm going to minimize this for a second. First things first, when you log into either the app at BlazingSQL, BlazingSQL.com, you need to sign in with your credentials, Google credentials, but you should be seeing something similar to this. So if you go to Welcome to BlazingSQL Notebooks and Webinars, if you do not see GPU_BDB folder over here, you will most likely have to pull the repo, refresh the repo. So this can be achieved by, if we see, we need to go inside the welcome and then just do git pull. That should, in all fairness, help and bring in the GPUbdb folder. In my case, this errored because I've already changed a couple of things in the code that I've been using here. But in your case, if you don't see GPUbdb, this should be straightforward. If you do not, please reach out to Rodrigo. He'll help you he'll walk you through how to bring you up to speed. That requires just removing the welcome Blazing notebooks and then just cloning the Git repo. But that's pretty straightforward as well. I'm gonna close this and go back to my notebook here. I am going to minimize this. So after you've cloned, I forgot one thing. After you've cloned this, you should see GPUbdb notebook and highlight code script. We actually need to add, let me make this a tad bigger, this GPUbdb runner egg. And that is available from our S3 bucket. I will share that in the chat.
Put the link in the chat.
Yeah, I'm just trying to get there. Oh, you already did?
Yeah.
Awesome.
I put it in the
Awesome.
chat.
Awesome. Thank you. All right. So we need to download that. You guys need to download that and then just literally drag it into the main folder, because we need to use that. That's pretty much the whole BlazingSQL. We packaged it up. So for us, running these enterprise scale use cases, we kind of benchmark how well we compare with others and within the whole Rapids ecosystem. So we ended up, packaging the whole thing into more maintainable, package. So later on, we can actually, just quickly run query number one query number 10, and provide some more unified interface for running those benchmarks. And you can actually see them, over here. All we need to do is to start the runner with some parameters and then say, okay, well, we'll just run query number 23 or query number 1 or query number 3 and so on and so forth. So we ended up packaging it up. That's why we need to upload this egg file and actually put it. So I'm going to start running this, put it on the path. So everybody, your Jupyter notebook can actually load this in. So in this case, we're going to, load up the runner and some other additional code that we're going to use throughout the webinar. I'm not going to go in particular detail through all of these config options. One thing that I'm going to point out is the network interface. If you are running in Docker, that would be a different network interface by definition. And underneath the hood, BlazingSQL should be able to recognize which network interface works best for your use case. In this particular case, since we're running on AWS, we are defaulting that to ENS5. Otherwise, it would create some other issues for us. But this is just a side note. So when you start the runner, I'm going to quickly just provide you a very quick overview of the runner class itself. So we are going to run on scale SF1. SF1 in our nomenclature means this is workloads that are around 1 GB every single time. What happens right now is we are starting the Blazing context. You can actually track what's happening. We've lost someone, I think. What happens under the hood, we actually right now launching a local CUDA cluster, and we are subscribing BlazingSQL to the S3 bucket bSQL. So you can actually see that info getting printed out on the screen. And then also our data directory. This is our bSQL bucket. This is publicly available data that we normally use throughout all the webinars. From the TPC-XBB SF1, we will be using the data that literally lives in that particular folder, and we'll be saving the data out to the TPC-XBB results.
Hey Tom, real fast. There's some commentary on your audio being a little bit low. Do you have any setting on your mic that might be limiting it?
Okay, let me try to see if I can actually change that. Bear with me.
You might have your test volume low, or your microphone volume low.
How about this?
On Zoom.
How about this? Is it better? Can I change it here?
I think the bit of the problem is I hear you too well. So
you hear me too well?
But it might just be my.
Okay. How about now? Like this is the only All
right. I think it's good enough. It's good enough. Don't worry about it.
All right.
Sorry to interrupt you.
Sorry about that. All right. So where were we? We have a runner running, right? So we have the runner running. So this is effectively our entry point to running all of these queries. So let's now focus on these queries. Like in this particular, in the hands-on part, we will focus on 2 use cases. Use case number 2 from that just effectively tries to find the top 30 products that are mostly viewed together with a given product in an online store. And there's a bunch of other parameters that we're going to constrain the query to. We have a session timeout of 60 minutes. They need to be viewed frequently together. the order doesn't match, and so on and so forth. Now, and then the use case number 23, where we calculate the coefficient of variation and mean of every item and warehouse of a given and consecutive month. And we will also only select the items that had that coefficient of variation greater than 1.3 over 2 consecutive months. There's all sorts of different use cases. We include them in the notebook if you want to run them. All of them should run end-to-end, with an exception of query number 27. We are working on bringing Spacy to be available in the free app. That this particular query requires Spacy, which is an NLP package for running in a distributed GPU world.
Real fast, just to give a little bit of context too. So this GPU big data benchmark that Tom is going to be walking us through is for a data set that's pre-generated from a data generator that represents or mimics a retail organization. And so that retail organization has in-person stores as well as online stores. And so there's a lot of reviews and unstructured data that's associated really heavily with the online e-commerce presence. But there's also a lot of transactional information on both the e-commerce as well as the in-store presence. So when we're talking about these questions that these use cases are asking, find the top 30 products that are mostly viewed together with another given product in an online store, that's the problem space that we're talking about for a retail organization and their particular data sets. And I'm just going to add a link to the repo that really kind of has a lot of information on this from the Rapids AI team. So I'll just put that in the chat. Sorry to interrupt you, Tom. I just wanted to give a little context.
I was actually getting back to to explain that, but thanks for jumping in. Awesome.
Mea culpa. Sorry.
No. It's all good. It's all good. So how would we normally solve this, right? So if you are running, a SQL engine, right? And if you had access to a, I don't know, SQL Server or Teradata or whatnot, it can be MySQL, you would start probably running this, this query in a very, very familiar way, right? So we would select the items, from our web click streams. We would select the user, we would select the item, and we would select the timestamp for, to create this table, right? So we will have 3 columns: user, item, and time in seconds. And then what we need to do is we need to sessionize that, right? So we want to, at the end of the day, select, 100 items where they appear in pairs, right? Within a the same session, right? So that's what they ask us to do. We want to have mostly viewed together, products with a given product in an online store. So that's why we only look at the web click streams. There's, as Rodrigo mentioned, in this particular data set, there's multiple, tables that, we are able to query. But in this particular case, we focus on the web click streams. And then, as you might already remember, for those of you who are attending, first time, every time you run a query against the BlazingSQL context, what we return back is we return either a QDF if we run on a single, GPU, or we return a Dask QDF, which is this distributed representation of QDF, so we can actually scale it up. In this particular case, this is a Dask QDF. So then we will map every partition to find the distinct sessions for every single user and every single item. So later on, we can actually select those items that frequently co-occur together. So what does the get distinct sessions look like? So if you're familiar with pandas, this code should be relatively straightforward. First of all, we hand off. So when you call map partitions, it automatically passes as the first argument, it passes the data frame. So every single in the Dask is effectively a collection of QDF objects, right? So QDF data frames, just like Dask data frame is a collection of pandas data frames, Dask QDF is a collection of QDF data frames. And when you call map partitions, the first argument is always going to be the data frame itself, either QDF or pandas. And then that follows with the additional parameters. So we will call get sessions method first, passing on the data frame itself. So every data frame is a single partition, and then we return that data frame that we get from the get sessions with, in the meantime, dropping duplicates. So the get sessions, the way this looks is we have our data frame passed by. So we sort the values by user and timestamp, and we reset index. That's a tiny, tiny thing over there. But what we are trying to achieve is to have the data frame ordered by user and by the timestamp. We don't care really about the items right now. We only care about the user and the timestamp. Why? Because we want to get the session ID. Every session, what it means is that, okay, well, if in the data, if I'm switching between users to the next user, of course, that session shouldn't carry over to the next user. That's one. And also we have a timeout. You remember that from the question we had, the session timeout is 60 minutes. So anything that goes longer beyond 60 minutes would be assigned as a new session. We would start a new session. It means like you walked away from the terminal and then you came back after 60 minutes. It will be a next session for you to browse the web. So let's look at the get session ID. This is pretty much what the core of things happening when we do the sessionalization. So first of all, we check, okay, did the user change? So if you go through the data set and then there's a change in the usernames, of course, we will flag that as a session change flag, and that actually appears over here, right? And then we calculate the time delta. The time delta, we compare that. So there's a very neat function. I actually pulled it up here. Whoops, can I do this? Yeah, there you go. Pull it up here from the docsrapid.ai. The diff function is a serious function that calculates the difference between the values at the position I and the value at the position I minus n. In this case, periods equals to 1, right? So what we can do is to calculate, okay, we'll take the difference between this value and the value right above that. That's why it was important for us to sort the values by the user and the timestamp in seconds. And then we check, okay, is this session currently timed out? So if we say the session timeout is true, if either of these two conditions are true, session timeout or flag, we say this is a session change flag. So we need to, that's going to be a start of a new session. Either that's going to be because the user changed in our data, or it was the session timeout. And then the rest that follows is relatively straightforward. We effectively create a time index. CP here, this is a CuPy array. If you are familiar with NumPy, CuPy is nothing else, slightly less functionality than NumPy, but nothing else but a NumPy that runs on GPUs. And we actually push that over to a get session ID from session boundary. This particular method, I don't have it listed over here, but what it effectively does is it assigns a numeric value to, okay, well, this was session number 1, 2, 3 for this user. Not really very interesting to walk through that. And then eventually we return the session IDs. Now bear in mind that this happens for every single partition in your data frame. So this this gets distributed to as many worker nodes as you have and as many partitions as you have. So that's the beauty of that. Now and eventually, once we get the sessionized data frame back, where we're going to have users, an item, and the session ID flag, we can then start, and then create the final table that will return the top 30 products that are mostly viewed together with a given product in an online store. So that's pretty much what this query does. So if you run this, bear in mind that we are running on 1 GB data set, right? So we're running query number 1, and that you can start to see that we're doing some operations on the GPU. Our memory utilization goes up a little bit, but it shouldn't take too long. Yeah, there are 15 seconds to actually run this query. 1 GB of data, all of these operations that happen behind the scenes two SQL queries and some partition mapping that that happened behind the scenes. Now, this was actually most likely due to to the data transfer. So if you rerun that, it actually should run a little bit faster from my memory. Yeah, 3 seconds, because all of this data has already now been persisted on the worker node. So if you run, let's say your use case is, okay, well, I have this data set that I want to explore. You actually need to if you bring this data to the work to the cluster that you run on, it automatically, you bear this cost of bringing this data and loading that to your local machines only once. Every single time after that, it's going to be almost instantaneous. All right. So this is use case number 2. Now, use case number 23 is actually a little bit easier to understand, because it literally is pretty much just SQL queries, right? So what we are being asked? Well, first one is calculate the coefficient of variation and mean of every item and warehouse of the given and consecutive month. So what we do first, we are going to extract the items from the inventory for a specified year and specified month. That's normally predefined in the description of the query. So we get that. And running this particular query retrieves the warehouse item, quantity on hand, and date, month of the year. Next, what we do is we will calculate the mean of the quantity on hand, right? So this is the next query here. From the inventory dates, which is this result, we can create a table. BlazingSQL automatically registers that table. It's already pushing that, and then we can use that that query, that table that was already created by the query number 1 in the subsequent queries. So what we do here, we effectively group by warehouse item and month of the year. You can see that here. And we are calculating the mean of the quantity on hand. So that's what happens here. And we can create this mean result over here. Now, the second query, the third query, what we are going to do here is to actually calculate the standard deviation of the quantity on hand. The way we calculate this here is we pretty much, this is implementation of how the standard deviation is defined. We sum the deviation from the mean of every single quantity on hand, square that, and divide it by the count of how many items we have, and then take a square root of that. So that's we now have access to the mean of the quantity and the standard deviation of the quantity. The next step is to calculate the coefficient of variation. The coefficient of variation is defined as a standard deviation divided by mean, and is a measure of how much spread you have away from the mean. It kind of gives you the the feeling of how this distribution would look like. So if you have the use case where your mean is 10, right? So you have normally 10 10 items on hand, and your standard deviation is 1, so it varies 1 to each side. Then your coefficient of variation will be 10%. So you can expect kind of like it's going to vary 10 plus minus 10%. If you follow the the 3 sigma rule, that's probably going to be more closer to 7 and 13, but that's beyond the point. That gives you some feeling of, okay, how much this is going to vary. If your mean is 10 and then the standard deviation is 10, it means that it varies 100%, right? So that's what it effectively means. And what we are being asked is to find the items that had a coefficient of variation of 1.3 or larger in the given and the consecutive month. So that's pretty much what we do in this query here, right? We select the item, we select the warehouse, the item, the quantity, but the whole idea of what we are selecting So the selection of the 1.3 happens here. So we only retain the the items that had the coefficient of variation of greater than 1.3. And effectively, after this, we used an inner join to create the final table that will have items that had the coefficient of variation greater than 1.3 in both months here. That happens when we join do the inner join on the inventory warehouse item, the month of the from the inventory 1 month, the current month, and then inventory 2 table, the alias of month plus 1. So we can run this. That should be actually also quite quick. And in the meantime, I will start this while we talk about that. Okay, so that took 9 seconds. Most of the other use cases, they are, if you actually scroll down, you can see that most of these use cases are kind of business use cases. This is a normal questions that a business running a online website and stores would ask their data analysts, data scientists, to optimize their business operations, right? So find 100 products that are sold together frequently in given stores, and only products in certain categories that the business is interested in that are sold in specific stores that should be considered. And sold frequently means that at least 50 customers bought these products together. So this is the questions that as a data scientist or data analyst I would get from the management, and given the data that I have in the tables, I would have to then work out, okay, well, how do I answer these questions? Most of these use cases are like that. There are a couple of other ones, and we will go through those on the 1 terabyte scale example. For instance, use case number 10, for all products, extract sentences from its product reviews that contain positive and negative sentiment, and display for each item the sentiment polarity of the extracted sentences, right? So this is more a natural language processing exercise. And you would probably have these types of use cases as well if you if you go to work in this kind of environment, business environment. We, I think, go through use case 23 we just did. Use case 28 is building text classifier for online review sentiment classification. So once again, we back into the NLP realm, where we try to build actually a text classifier. We have some labels that we've previously assigned, and then for the new incoming reviews, we want to know how would we classify that, so we can present the values, to present the data back to the leadership, so they can understand whether we're doing better, we're doing okay, or there's something actually broken and we need to fix that. So if you scroll through all of these, they're actually quite interesting on their own. So I would also highly encourage you to go and check them out, run them. You can run all of this code in the free app, as we do currently over here. This is all going to work, and then you can check how quickly it runs, and also how easy easy this is. You can pick inside the source by using this the inspect package from Python. The print code helps you to, I didn't talk about that, but this small piece of code actually helps you to print out the code into the Jupyter cell with highlighting, so it's a little bit more readable. Okay, let me check if we are ready. Oops, not this one, here. Okay, we are running, so let's get this started. This use case and this particular, let me make this a little bit bigger, I think. There you go. All right. we are currently running on a cluster that has 64 GPUs, and this is running. We will be running on a use case, as I mentioned, on one terabyte. So I'm going to start, running this. Let's see if we already have all the 64 clients. We have all the 64 clients. When you start task, when you instantiate the client, when you use a private GPU cluster from BlazingSQL.com, we automatically start, we automatically start a Dask cluster for you. So you can tie your client to the cluster that's already running on the cluster. Normally the address is, the port is 8786, and we expose that on the local host, so you don't have to that's the change that when we started, we normally would use the IP. Okay, so we will start 1000. So this is in this nomenclature, this is 1 terabyte, data set. The change here is that we actually have a already running Dask cluster. We don't want to start a new one. So when you specify the scheduler IP and port and tie it to localhost 8786, the runner will attach itself to that particular Dask cluster. And another change is that we are using pull to true. This helps to speed up things running using cuDF. Underneath the hood, we are using the Rapids Memory Manager to manage the memory allocation and deallocation, also as well the garbage collection after each run. So I'm going to start this. You can see that we are right now initializing BlazingSQL. That will take a little bit of time. But one thing that we also need to do is that the code that you run on every single partition, once it's packaged, it needs to be delivered to every single worker. So every single worker needs to have access to the same code as you have on the client submitting the job. So Dask has this nice functionality that if you package your module into an egg, this is when you do setup.py, you create your setup file. You can actually run Python setup.py bdist_egg, and it will produce a distributed version of your package. And that's what we have here. So this is GPUbdb runner.egg. This is what we're going to right now deliver to every single client. And the client we have, so the runner has an internal property called client. So we can actually, this is the Dask client object that we're going to use. That doesn't take too much. Now, so let's focus on the use cases that we're going to walk through. So use case number 10, as I already touched upon a little bit when we were in the free app, is for all products, extract sentences from its product reviews that contain positive and negative sentiment and display that the polarity of each sentence, right? So let's pick inside that particular use case. So first of all, we are going to go to the product reviews table. We create a table from product reviews and all the Parquet files that are in that particular table. I'm actually going to run this first as we walk through all of this, because that might take a couple of seconds. It's probably going to be like 2 minutes, but we should be done by then. So first of all, we extract the items and the product reviews from our table. Of course, limiting that to items that we actually have a review for. And this is just literally cleaning up a little bit. So we are going to normalize the string to push that to every single character is low, in a lowercase, and replace some end of full stops, question marks, exclamation marks, and EOL char. EOL char is going to replace that. Oh, I don't have it here. It's going to replace the every full stop or any stop mark with a unified character, so we can then later on create the sentences from reviews, right? So that will help us to instead of checking for all of these in making the other code more complicated, we just unify that, and then we only check for the end of line character. And then finally, what are we going to do later on is we are going to create the words from sentences. So from every single sentence that we've already partitioned in the map partitions here, we are going to extract the words from that. So later on, we can actually join that with a negative sentiment and positive sentiment words that we have already stored in the resource list directory. This is coming from the official PCXBB kit, and we just trust that that's what's there. And then finally, we are creating this word underscore data frame table that we extract the review sentence. So for every single item and every single sentence, we are going to extract the sentiment and the sentiment word from all from this inner join here. So all of this, gives you. Let me run this. Oh, we are currently blocked, so it's running. So you can see that we have 64 partitions partitions running. We are currently waiting for them to finish. Let me see if I can make this a little bit bigger. Right now, we are occupying 200 gigabytes in memory. This is not necessarily indicative how big the data is in your in memory or on disk, sorry, because Dask will handle that very gracefully. Like if you cannot load everything into memory because you are limited there, it will actually do quite a bit of nice tricks in order to keep it organized and not run out of memory. There. So we finished processing. What happens now? So for every single use case, we actually save the results of running that use case to a results table. So you can see query number 10 is currently running. So that's why writing out the results to the file. So later on, you can actually go inside and pick what we've done. Have we done what we were asked to do? So this is probably one of the queries that is producing a little bit larger results. So that will take a little time, but it shouldn't be too long. Now I'm going to walk you through how we actually do this in query number 10 over here. So create sentences from reviews, as as we talked. Let me close this. Before, we are checking for the end of line character, right? So we are using the tokenization functionality from QDF that checks for the delimiter that is end of line char, right? So this will produce. If you have a review that is 10 sentences, effectively what this particular call does, it will produce a data frame, a time series, a series with 10 elements associated with that particular review. And then we do a counting. So we just count how many tokens there are, and then effectively return a sentence data frame. And same thing for create words from sentences. We replace everything that is unnecessary that we don't want to see. You can see that commas and semicolons and dashes and whatnot are replaced with null character, and then dot is replaced with the space. We normalize spaces and count the words. So we essentially return the word and the global position as the return from this query. So let's see. Okay, this has finished. It took 250 seconds. I guarantee that would have been faster than that if you rerun that, and we're not going to do that today. And these are the methods that we just went through. Let's pick inside, see if we can actually see what we produced. This is going to be quite big. Probably might have been smarter if I just did the terminal. Let's try that real quick. Come on. Okay, that doesn't want to run for me now. I think it's got stuck because I tried to open that. Let's move on. We might come back to that later. Okay, there you go. So where are we? CD webinars. Q10. Oops. Okay. So we have, it looks amazing. It's assigned sentiment is positive, and the sentiment word that determined the sentiment was actually the amazing. And most of these, let's try tail, see what's there. This is still, most of them are positive because of these chosen words. Okay, so you can see that it's actually running and running well. Now, for the use case 20, the customer segmentation, right? So what we try to do is to create a segmentation model that focuses on the frequency and the order ratio, item ratio, in order to determine the different clusters of customers. So I do have the, how we are going to, how this is all happening underneath the hood, but I'm not going to walk through this because I'm mindful of time. So I'm going to just run this. This shouldn't take actually that long. I believe this is around 50 seconds. What happens here, and I'm actually going to open that here while this is running, to show you what we do, right? So first of all, of course, we create the store sales table and the store returns table. We extract the customers, the users. We create the order ratio. So a bunch of case statements where if it's null, we don't want to divide by 0. If it's 0, we don't want to divide by 0, and then just default that to 0. So effectively what we do here is we are creating all of these the vector vectors that we're going to distinguish the dimensions along which we're going to separate our clusters into. This is literally just one single big query that creates all of these features for us. And then we hand it over to this get clusters method that runs here, and it builds a clustering model. So this is building a k-means model that runs in a distributed way. So that's why we have all of this delayed functionality from Dask that actually does that and trains the model uses all the workers to train the model. And then effectively later on, we just return the user and the label, so which segment that goes into. I think this might have finished right now. Okay, took 62 seconds, and here's the center of the clusters. We found 8 clusters. So this is pretty much what we would expect from this. And now we can build the text classifier. I'm going to start running this as we talk. The code, we can actually look over here. That's going to be easier. So what we are asked to do is for every single review rating and content, we extract that data. So we split that over here, right? So first of all, we split that into 90% of the data we're going to use for training, 10% of the data we're going to use for testing. And once we have this data, extracted, we pass it on to the post-ETL processing. So post-ETL processing is effectively here. What we are going to do in this particular use case is we are going to use the CoolML and the naive Bayes algorithm. But as you can see, we are using a Dask naive Bayes. So that means that this particular naive Bayesian model is going to be trained on multiple nodes. So it's going to be distributed. And in this particular case, simply because we have positive, negative, and neutral sentiments, we are going to train a multinomial naive Bayes model. So first of all, as we always do, we do some feature engineering. We build the features. I'm not going to go in detail through all of this. All of this is, you can actually look up yourself if you want to. We're going to build the features. We're going to build the labels, and then finally fit the model, right? So we create an object for the model training. We pass this to the client that we've used, and fit the model, and then do the prediction. So prediction. We are returning that particular final data back to the user. So let's see if this has finished. Oops, what happened here? Did I crash? So that was query number 28. It's still running. Oh, it must have crashed on me somehow. I don't know what happened. So let me quickly restart that and run only query number 28. Okay, 5 minutes. We should be good. Okay, let's create that and upload our. This is now much quicker because we already, had that running before. So let's run this again. This should be quicker now. We must have hit some sort of a use case or some corner use case that prevented us or crashed that. This from memory, if I remember correctly, it also takes around 60 seconds. So I keep repeating that it only takes 60 seconds, but I think what I forget to mention that this is running on a 1 terabyte data set. So it takes 60 seconds on 64 GPUs to process and build a classification model from scratch. So you can actually see that. We start really from scratch. We create a table. We extract this information. So we do the ETL. We do a cleanup of this. We build the features. We build the labels. We train the model in a distributed fashion, and then calculate the accuracy score, precision score, confusion matrix, and all of that happens. There we go. All of that happens in literally, 60 seconds, or close to it. There you go. So we have the accuracy 70 seconds. I was wrong by 10, off by 10.
And the data set is on AWS S3.
Correct.
In Apache Parquet, right? So it's coming over the wire as well.
That's right. And it's a really good model. I would be probably quite skeptic about using this model in production because something that is 100% accurate is probably, on the nose a little bit, but beyond the point. The point is that I'm trying to make here, I'm going to probably skip the use case 30 in lieu of, like, we have 5 minutes, so I'd rather have some, Q&A. But what the final point that I was trying to drive here is that this gives you the ability to use pretty much all the data that you have in an interactive way, build and train and test different models, because you have the results back in 70 seconds. So even you saw me, like, it crashed. Yeah, well, it crashed. I could go up, rerun the first five cells, restart this, and 70 seconds later, I already have a model built that I can, if I'm happy with this, I can deploy to production in no time. So that's the beauty of the way I see the cooperation between the BlazingSQL and Rapids. And if all of this, pretty much throughout this whole use case, we almost have never left the GPU. We did not incur any cost of moving the data from GPU to host, or if we were to run this workload on a CPU, I would be still talking, and I'll probably run out of the talk points by now about explaining the code. That's why I had to actually skip some things, because I know it runs fast, right? If I were to run this on CPU, that would be much longer. I'm going to only quickly touch. So the use case number 30, we performed the category affinity analysis for products viewed together online. So this is kind of very similar to the use case that we run in the free app. But you can also check it out. All of these use cases that we've shown here are also, if you clone that repo, you can try it out on a smaller data set, but still you can try it out in the free app. So I think I'm going to pause here. Rodrigo, do you have any questions?
Yeah, no. So there are no questions in Q&A, but once again, as always, that was awesome. It was really interesting to watch us go from 1 gigabyte to 1,000 gigabytes, and making it totally interactive. And really, there was very little code changes, even underneath, because I know we didn't go into like the runner itself and how the runner was built out, but there really isn't all that much changes to the code to enable it to work with Dask and distributed across these 64 GPU workers.
Actually,
so if anyone hasn't,
sorry, to drive that point, sorry to interrupt you. There's literally no change, right? So the same code that ran in the, runs on the 1 gigabyte, runs exactly the same code runs on the 1 terabyte. So there's literally no change between these things.
Awesome. So if anyone has questions, Alex is asking, can I run this on premises? The short answer is yes. We actually have pretty substantial performance improvements if you're running on, kind of modern this year's flavor DGX A100s or A100 GPUs. These queries that Tom's showing off that are taking 200 seconds or 70 seconds take more like 8 seconds or 5 seconds with on-premise servers. And there's really a lot of attractivity in leveraging those servers. Something else, if you could show the Blazing Notebooks page real fast. So this application that Tom is showing, we have this running as a managed cloud offering, but this is actually a fully packaged Kubernetes application that deploys very well to GPU servers, particularly DGX A100 servers. So this system that actually enables you to have a multi-tenant data science cluster, which is what Blazing Notebooks effectively does, lets you turn any group of GPUs into what we call a data science supercomputer. And so if you want to run this on premises, you're more than welcome to do it. We have a product offering that simplifies the deployment and the management of this stack. But even if you don't want to, you can do it entirely with the open source stack as well. In fact, there's some really great numbers too. Here, I'm going to find the blog post that shows off how we do on this benchmark with an on-premise system. Cool. And I'll put that in the chat.
You wanna show that, or?
Yeah. I mean, I can. Okay, yeah. Here, I'll take over.
Okay.
Oops. 1 second.
Yeah, you take over. I'm gonna mute this.
Okay, so if you can see my screen, I'll zoom in a little bit. You can basically see how our system holds up versus previous implementations of the GPU database benchmark. And you can see for doing the entire workload, so all 30 use cases, we do it in about 647 seconds, and that's with about $1.8 million worth of hardware. So there's quite a few, DGX A100 servers that have the 80 gigabyte A100 GPUs. We actually ran this on a portion of Selene, it's the world's 5th fastest supercomputer. And we got access to a few nodes on that system that enabled us to do this workload. But yeah, I mean, at 640 seconds across 30 use cases, we're talking an average time of about 20 seconds per use case. And I should have mentioned, this is on 10 terabytes. The thing I'm showing right here is not on 1 terabyte of data. This is actually a 10 terabyte data set. So excuse me, I didn't caveat things with that. So if you're talking about 1 terabyte, you need really quite a bit less infrastructure, and you can do fast analytics with this. I'll stop my share so I can see any other questions. Yeah, so we're over time. Tom, thanks again so much for a great presentation, great workflows. As Tom mentioned before, you can run all of this on app.blazingsql.com. You can watch this on YouTube later if you want to look at any particular part of the workflow and understand it a little bit better. And yeah, you're more than welcome to keep following us on Twitter, on YouTube. Please subscribe to our YouTube channel if you found this content interesting. We're really trying to come up with interesting content. Please let us know via Twitter or even, just emails, tom@blazingsql.com, rodrigo@blazingsql.com, what kind of content you're looking for, or what kind of use cases you would like to see shared on our webinar series. And if you have any questions about leveraging BlazingSQL in the Rapids ecosystem, please don't hesitate to reach out to us through all those different channels I just mentioned. And thanks a lot for joining us and watching this webinar with us. We really appreciate having you all here and sharing a little bit more information about BlazingSQL and the Rapids ecosystem with the world. So if there are no more questions, I'll just end the webinar. And thanks a lot, everyone, for all of you who were able to make the time and show up.
Thanks, everyone.
Awesome.